Okay, so welcome everybody for the talk today. So today we have the pleasure to hear Paulo Eduardo Faria Jr. from Regensburg. And first of all, thanks Paulo for accepting the invitation. And I'm going to give a brief introduction about Paulo. So he graduated in São Carlos at IFSC in 2009. And then he did his master and his PhD in the group of Guilherme Sipai over there as well, finishing the PhD in 2016. And soon after that, he went to Regensburg to work as a postdoc fellow in the group of Jaroslav Fabian. And since then, his career grew up quite quickly with very nice publications, very interesting works, particularly with G-factor and excitons, very interesting and very interesting work to see. So let's hear today Paulo talk about his recent works. So thanks again, Paulo, for the invitation, and now the mic is yours.
Thank you, Gerson. Thank you for the introduction, and thank you for the invitation. Also, thanks, George, that is not here, but also for the invitation and setting up the devices here so that this can work. So in my talk today, I would like to discuss a little bit about the Zeeman signatures in van der Waals heterostructures and two different phenomena that can be observed like that. One related to effective G-factors and the other one related to proximity exchange. So let me first start telling you about the system and the van der Waals in two-dimensional materials. And to use as an example, I show here graphite. And graphite has this layered structure. And what is interesting about it is that in the plane of the graphite, in the graphene plane, we have in-plane covalent bonds, whereas in the out-of-plane direction, the layers are glued together by the so-called van der Waals interactions. And this is one typical natural crystal of graphite that you would find. And if you do the so-called mechanical exfoliation technique, then you start peeling off the layers and you get something like this. These are few layers of graphite, but if you do this process a few times, then you get graphene, which was awarded Nobel Prize of Physics a decade ago or so. Not only graphite has this kind of a layered structure, but many other materials in nature. And nowadays, we can find whatever property or almost any property that we would have in 3D. Also, we have an analog in the 2D world. So for example, graphene, the 2D layer of graphite is a semi-metal. We have niobium selenide, which is a superconductor. We have chromium triiodine, which is a ferromagnet. We have insulator, boron nitride, and semiconductors and topological insulators, and many of these interesting properties. That perhaps the most interesting advantage of also investigating van der Waals materials is that we can combine them. We can choose different materials with well-defined properties and combine these two properties to get the both out of the best property out of these two worlds. So this is the concept of van der Waals heterostructures, which people usually make an analogy with Lego blocks. But these are special Lego blocks because they not only can be stacked on top of each other, but we also have very important effects that are related to shifting one layer with respect to the other, and also twisting one layer with respect to the other. But if we look at, let's say, just at the interface between two materials that may coexist in this heterostructure, basically, to understand this interlayer coupling, we can have this perspective from the electronic density. So each layer will be in its ground state, will be characterized by this electron density. And this region where this electron densities overlap is what would give rise to the interlayer coupling, which of course will be spread throughout the many bands of the material if you're imagining a band structure perspective. But what I would claim is that because of this interlayer coupling, we have emergent physical phenomena interesting emergent physical phenomena coming from these van der Waals heterostructures. As an example, I would say superconductivity in twisted bilayer graphene, completely unexpected and just generated by taking two graphene layers, putting on top of each other, and rotating these two layers by this magic angle of around 1 degree. So superconductivity is an emergent phenomena from twisted bilayer graphene. And another example, more related to optics, which is what I do more often, is the so-called interlayer excitons, where by combining different materials with different band gaps and therefore generating a different band alignment, this spatially separated electron hole pairs can also interact and give rise to this so-called interlayer exciton. The materials that I'm interested in the most are the so-called transition metal dichalcogenides. They will be the platform to explore this Zeeman splitting physics. And these materials have hexagonal crystal structure, like this one. And if you go from the bulk to the monolayer, then what people observed was that this material becomes a direct band gap semiconductor, down to the monolayer limit. This has been demonstrated experimentally and also observed in density functional theory calculations. And interestingly, the band edge here, where the direct band gap happens, is located here at the corner of the Brillouin zone, at the edge, at this vertex of the Brillouin zone, what we call the K valleys. Because of this direct band gap nature, and also because of this reduced dimensionality of the 2D materials, the optical spectra is ruled by excitonic features. Excitons are the electrons that are excited to the conduction band interacting with the holes in the valence band electrostatically via Coulomb, in a simple picture. So you have some sort of hydrogen atom picture. And then this picture holds, you would observe excited states, and then optically it is possible to observe the 1s, 2s, 3s, 4s, and depending on the quality of the sample, many excited states in this kind of materials. If we are thinking in terms of spin and orbital degrees of freedom that are entangled via spin-orbit coupling, we also need to include the valley degree of freedom. This is the low energy band structure of these materials, and the spin alignment at K is reversed with respect to the minus K. This is a consequence of time reversal symmetry. These materials are not magnetic. So whatever happens at K, if you apply time reversal symmetry operations, you find the analog at minus K. And what is interesting is that these optical transitions that happen at the valleys are circularly polarized, and each valley holds a different circular polarization. And this has been demonstrated here experimentally, where the excitation was performed with one polarization and then measured with opposite polarizations. And then we see that if the polarization matches the excitation, we observe the signal coming out from one of these particular valleys. And in this material, I would also emphasize that valley and orbital degrees of freedom are very intimately connected. So sometimes it's not possible to really disentangle what is really coming from valley, but it is just a consequence of orbital degrees of freedom that are manifested in around this band edge. And these materials, when we start combining them with van der Waals heterostructures, they offer very interesting opportunities to study the coupling of all these degrees of freedom, the spin, the valley, and the excitonic as well. Here I'm showing the low energy band, and at each valley we have different bands, conduction and valence bands. Each of them are characterized by their orbital and spin degrees of freedom, and each of these valleys can host excitonic effects. And to investigate or try to disentangle what is orbital, what is spin, what is excitonic, we can use the valley Zeeman splitting. And valley Zeeman here essentially means that we are breaking the Cramer's degeneracy between K and minus K valley. So bands here at K shift in opposite direction than at minus K, and then by analyzing this energy difference, we can have very interesting insights from the materials. And one way to achieve this valley Zeeman splitting is using the so-called effective G factors, which are the splitting because of an external magnetic field that you apply to your structure. Or nowadays we also have this ferromagnet to the materials. Then we can couple the TMDC with a magnetic substrate, and the consequence of this energy splitting is basically coming from what we call proximity exchange. So I'll discuss these two things, and let me start by discussing effective G factors in these TMDC materials. And that's basically what we have published here in these three papers. To discuss the valley Zeeman in these materials, we have to go back to the foundations of G factor physics for block electrons. So imagine we have a crystal in 3D for simplicity, and it is defined by this band structure here. Let's say we're interested here in the bottom of the conduction band. So by zooming in, we see the two electron branches, time reversal partners of each other, not necessarily with this splitting. This is I just shifted for clarity to emphasize the two branches. If we start applying an external magnetic field, for instance, in the out of plane direction, each of these branches will experience a Zeeman shift in opposite directions. And it is often that one defines the Zeeman this difference between Zeeman shifts of one branch and the other as the Zeeman splitting. But what drives the Zeeman shift of one of these bands is the so-called G factor, this G of Z. It depends on the band N and the point in the Brillouin zone that we are, the K. And this G factor is actually the sum of the orbital and spin degrees of freedom, which I'm going to call L and S. And just to clarify that block electrons that I'm having in mind are actually after having spin orbit coupling in the calculation. So this wave function is really a spinor with contributions with spin up and spin down that are in principle different than each other. And these different contributions can be investigated by the spin angular momentum, which essentially means that we evaluate this matrix element here. So if it's in the out of plane direction, we have sigma z. If it's in any other direction, we have combinations of Pauli matrices. And because of spin orbit coupling, this matrix element does not necessarily give you plus or minus one. It can be anything in between. And this is actually one of the consequences for spin relaxation in materials in general. So for example, for graphene, with this very weak spin orbit coupling, we have showed that this is indeed the case behind some of the expectations that people had in terms of spin relaxation. And here in the group of Professor Jaroslav Fabian, they have investigated even different materials, for instance, platinum selenide or graphite, many layers of graphene, using this kind of understanding that you get from the spin angular momentum. For the orbital angular momentum, or sometimes also referred to as the self-rotation of the block electron, can be described in two different ways, but equivalent, because you go from one to the other. This one in green, it starts from having some knowledge of the Berry connection in your material, and then you end up with derivatives of the Bloch function with respect to K. You can go from this expression in green to the one in blue, which is basically a summation over bands, general for any K points. And if you are at the band edge, then this is basically what people have been doing since the late 50s, using the K.P perturbation theory. Since I'm talking about excitons, basically the G factors that I want to compare or understand are basically being probed optically. So let's imagine we have this crystal here with this out of plane magnetic field, and there is a laser pulse coming in and a light coming out of the material that can be resolved in different circular polarizations. And basically what people would see then in the experiment is that the spectra for one polarization is shifted with respect to the spectra with the other polarization, and they would define the Zeeman splitting as the difference between these two energy peaks. And that means when we are looking at conduction and valence band transitions, or imagining that we have an exciton generated by these two bands, we are looking at the net effect of conduction and valence band G factors. And to really observe such a Zeeman splitting, let's say the the most fundamental prerequisite that we need is that conduction and valence band effectors are different. Once that is achieved, very likely there will be a Zeeman splitting happening in the optical spectra of the material. And this is the way that exactly how people measured this, the Zeeman splitting in TMDCs. They started with a monolayer on top of a substrate, applying out-of-plane magnetic field and collecting this excitation with resolving with sigma plus and sigma minus. What they observe is that indeed, when there is a magnetic field applied here, you see a shift of the energy peaks. Here you also see the different peaks that are related to tryons, which are composite quasi-particles made out of 2 electrons in one hole or 2 holes and 1 electron, depending on how is the doping in the sample that you have, or you can even tune that with external gates. But then this is another peak that one would observe also in the experimental spectra. If you look at the energy separation, then you see a very nice linear dependence. And basically, the contributions of opposite polarizations are coming from different values. And in this TMDC community, they, instead of saying Zeeman splitting, they often refer to it as the valley Zeeman splitting or the valley Zeeman effect. And the way they started describing this phenomena in this publications around 2015 was that you could decompose your G factor into 3 components: a GS for the spin, GV for the valley, which they also said this would be the self-rotation, and GO for the atomic orbitals, which are the more related to the D-like character of these bands around the band edges. When you combine these values and you try to calculate the exciton defector, then everybody was getting suspiciously values of around -4 that were matching the experiments at the time. But the main problem with this picture is, first of all, self-rotation is for the Bloch angular momentum, and the Bloch function already contains atomic orbitals. So that means this picture you can, if you have ever seen this before, please forget about it and just remember the 2 equations here in blue together with this information here. That is very fundamental and applies not only to TMDCs, but to many different materials. So then why people were not getting this, why did they not use this picture? And the problem was that they did not properly evaluate the summation over bands of the orbital angular momentum, which is the following. So here is the LZ for these different bands here of this TMDC material called tungsten disulfide. And when we start increasing the number of bands that enter here in the summation, we see that it requires quite a lot of bands, up to 300 here for a good convergence, in order to really find some good values here for the orbital angular momentum. And if we combine that to investigate the G factors of the A and B excitons, which experimentalists have access to, then basically not converging the orbital angular momentum underestimates quite a lot this G factor value that you calculate. And perhaps this was one of the main reasons why they started to include other effects such as this orbital degrees of freedom and so on, atomic orbital part. Interestingly, this has been independently demonstrated not only by our paper here, but by these other 3 different groups, and they all achieved the same results. If you really want to have very good values of this orbital angular momentum, good meaning converged, then you really need to take into account your number of bands. And I get asked a lot on the reason behind this number of bands. So why do we need so many bands? So my answer to this question now, at the time this was not very clear to me, but I would say the physical reason for this band is that when we're doing this calculation, at least with the DFT code that I'm familiar with, we place the monolayer surrounded by vacuum. And in this vacuum region, you would find a lot of states, unoccupied states, that behave like plane waves. And these plane waves do not effectively interact with the atomic states that are in the band edges of your TMDC. But some of these unoccupied bands have well-defined atomic character. So we see here in this plot, in the bottom part, I'm decomposing the wave function into a sphere around tungsten, a sphere around selenium, and a sphere and whatever is living in the rest in between. And basically we see that when we go to the unoccupied regions, there are some spikes of, let's say, atomic information. And whenever we have a spike, we have one of these jumps here in the orbital angular momentum. So that means when we don't have spikes anymore, for instance, around this region where the wave function is basically plane wave, then we stop to see jumps. So the point is that in this basis set that we are using that requires plane waves, there are many states that are not effectively coupling to the atomic states. And actually, this is a general feature, and I would like to advertise our paper with Gerson that will be on archive tomorrow. So, but if you still cannot wait for tomorrow, then you can have a look at the GitLab webpage. That we investigated not the orbital angular momentum, but the effective mass parameters, meaning that the curvature of these bands, which have an opposite sign here with respect to the orbital angular momentum. And what we saw is that indeed, to find a good convergence, you need roughly 300 bands as well. And in this case, we also use this basis set with plane waves. But regardless of the basis set, there's nothing here in the formulation that limits your summation. So you have to be consistent with the summation and the basis set that you choose to describe your problem. Once this is done, you can converge the values either from the effective mass parameters gamma here, or for the orbital angular momentum in these TMDCs. To really show that this convergence leads to realistic values, here I'm showing two comparisons with experiments, one for tungsten diselenide, the other for tungsten disulfide. I'm plotting the ratio between the theory and the experimental G factors. So one would be a perfect agreement, and the thickness of these lines here are essentially the experimental error associated to these values. These experimental works were able to not only measure the A and D excitons, so two different types of excitations that are connected to different bands, but they were also able to disentangle conduction and valence band G factors and extract the band G factors purely from optical measurements. And then what we see here is that the calculations match quite well the experimental values. So we can faithfully reproduce the experimental signatures of G factors in the bands, in the band edges of the TMDCs. And this gives us confidence to apply this to other systems. And here I'm showing hopefully the most up-to-date references that have been using this approach within first principles to investigate physical phenomena beyond TMDC monolayers. So we have done some strain works investigating what mechanical deformation to the monolayer, how the mechanical deformation affects the G factor. There are some strong works here investigating defects which are present in nearly all the TMDCs. Some interesting works here on the doping. Many works on van der Waals heterostructures. That's something I want to discuss in a few slides. We also have looked at bulk TMDCs, particularly for this unusual in-plane G factors, which is not something that is easy to probe in these materials. And we even investigated other compounds that behave like a TMDC, but are have more atomic layers. And the approach works quite well. And more importantly, the approach reveals very interesting physics for each of these particular systems. So moving to van der Waals heterostructures, I want to start discussing this type of TMDC van der Waals heterostructures here, this MOSC2 on WSC2. This is interesting because one can observe the interlayer excitons. So these interlayer excitons are coming from optical transitions from the top of the valence band, which is from tungsten, to the bottom of the conduction band, which is from molybdenum. And then, although there is a weak dipole matrix element between these two, there is a strong signature in the optical spectrum. And people have observed that when you start measuring the Zeeman effect in this interlayer excitons, it is very sensitive to how you stack your heterostructure, either if you try to do with 60 degrees or with 0 degrees. So to really understand this kind of spin valley physics, we need to take into account that these materials are sensitive to twist angle and atomic registry. So twist angle meaning that we rotate them by 0 degrees. This is what people call the R type, R from rhombohedral stacking, and 60 degrees, which people call H type for hexagonal stacking. And we can also do in-plane shifts on this, how these materials are aligned. And each of these shifts can be, let's say, labeled using the following notation. So this S here would be R or H. The sub-index would be the bottom layer, which for reference, I'm going to use the hollow position of the hexagon. And the top layer can move to M, X, or H position. M for metal, X for the chalcogen atom, and H for the hollow position as well. And it's important to investigate these stackings because on one hand, they appear in the Moiré potential as high symmetry stackings there that you could use to interpolate and generate some sort of continuum model. For some conditions, these materials do not create a Moiré lattice, but they create what we call atomic reconstruction. And that means there are large regions with a well-defined symmetry stacking appearing in the heterostructure. In real life, in one of the samples, you can get the two things, Moiré or atomic reconstruction, and you can even have much larger regions with a single atomic domain if you have some side edges constraining your heterostructures. So this has been experimentally demonstrated that it is very important to understand the behavior of these high symmetry stackings. So what we did was to consider these most relevant ones, the ones with the highest symmetry, for 0 and 60 degrees with some lateral shifts. We computed the band structures to obtain the G factors, and more importantly, to also have a look at how the optical selection rules change from stacking to stacking. And basically, optical selection rules will tell you if your G factor will be positive or negative. And basically, rotating the top layer with respect to the bottom layer, we are aligning K to K values or K to minus K values. And this, of course, reverses the spin degree of freedom here in the conduction band if we are keeping the bottom layer fixed. And in the G factors, we do see that each of these stackings are imprinting not only different magnitudes, but also different signs. And to compare with experiments, there are these two stackings that are the most relevant ones, the ones that occupy a large area in the sample and have the most energetic favorable emission. And then we see that what we calculated matches quite well with the available values in the literature, both for 0 and for 60 degrees. And here again, we did the summation over bands approach, properly converging the bands and extracting these G factors. These interlayer excitons are also quite sensitive to external electric fields, so applying a voltage drop across the structure. And that it will behave like an electric dipole, and the energy will shift linearly. And this can be quite interesting if you want to make devices out of this, so you can tune your energetic emission. So here's one example, and here's another example, and then here you see something more intricate, that there are different excitonic species, and each of them have a very well-defined electric dipole. So we decided to investigate this kind of effect and trying to connect with this spin valley and G factor physics. So I will summarize what we found for this stacking here in the interest of time. And basically, when we look at the low energy bands, we have this multitude of optical transitions, aka exciton species. And if we focus on how they shift with the electric field, then we see that KK excitons, here just direct in K, have the largest electric dipole moments, whereas the Q band, the KQ and gamma K have quite similar, and the gamma Q has the smallest one. And then this agrees quite well with this experimental observation that you have a lower energy exciton species with a decreased electric dipole moment. When we looked at the G factors as function of electric field, then we saw that KK excitons are basically not changing the G factor. So over this range of electric field, you have nearly stable values. Whereas whenever we have the Q band interfering with your exciton, then the G factors change quite a lot, from around 4, and this is more than enough to be experimentally observed. And perhaps using this information, one can really disentangle what are these excitonic species here in this heterostructure. So one just need to take this sample, apply an external magnetic field, and see how the G factor would change with respect to this applied electric field. And the physics behind these changes are basically the bands are interacting when you start to apply electric field. So here I'm showing the conduction band, here I'm showing the valence band at the K point, and here I'm showing this side bands at gamma and at Q. So whenever there is some crossing or in the orbital angular momentum, meaning that there's an interaction between the bands that is driven by the electric field, we see some signatures here in the exciton G factor. And actually, in similar systems, not necessarily the same MOSC2, WSC2, but systems that would have these crossings for different bands or happening at different electric field values, these features have been observed, for instance, in bilayer MOSC2. So we see here that there is a region close to 0 that the G factor is -4, and then it switches to 12, meaning that you go from an intralayer to an interlayer exciton because you are switching the bands around the band edge. In this other system here, they have observed this as well, but even more interestingly, there are some higher order effects, so to say, that the G factor not only gets more negative, but then it starts to come up again and then gets to the value here in the anti-crossing. So this tells us that there are for sure more higher order effects beyond this coupling of the bands that are playing a role here. The last heterostructure I want to mention in terms of magnetic field are these TMDC and graphene systems. And if you talk to someone in the graphene community, then perhaps they would say that I'm very interested in this kind of heterostructures because I want to investigate proximity-induced spin-orbit coupling, meaning that I want to go from my microelectron volt spin-orbit coupling in graphene to milli-electron volts. And you can do that by simply placing graphene on top of a TMDC. And this has been demonstrated to influence a lot the charge to spin conversion measurements that people did, and also allowed one to do optical spin injection in graphene because of this coupling to the TMDC and this modification of the spin orbit physics. So there are many investigations on this perspective. On the other hand, if you talk about these heterostructures with the TMDC community, they will say, yeah, graphene is a very nice material to engineer the energy of my excitonic emission. So here is the energy of the exciton as function of the number of graphene layers that you put on top of the TMDC. So the more graphene layers you add, the more towards the red the energy of the exciton goes. And that means effectively you are changing the band gap as well, simply by engineering this dielectric environment. What we started investigating was that the experiments by Andreas Thier and Scott Crooker, they have shown that G factors actually behave quite unexpectedly in these materials. So this is the optical spectra they found, and we see here the A exciton and the B exciton both do experience a redshift when we put the TMDC on graphene, or we encapsulate the TMDC with graphene, as we knew from the previous studies. When we apply a magnetic field, they have very large magnetic fields up to 60 Tesla. Each of these excitonic species nicely split, as one would expect as well. But when we looked at the G factors in more detail, we saw this behavior, a linear decrease for the A exciton G factor, and some sort of random jumps in the B exciton defector. For the A exciton, this dielectric screening that also affects the redshift of the energy is enough to explain why we see this behavior. Basically, increasing the dielectric screening squeezes the exciton wave function in k-space, and this consequently leads to G factors becoming more negative. But for this B exciton defector, it does not follow this behavior. And then we asked ourselves, could this be signatures of microscopic effects? Basically, as people looked in the graphene community, if we start to look at the heterostructure, including this coupling between graphene and TMDC, would we see some difference? And this is what we ended up doing. We considered a few different scenarios just to explore what could be happening. So we have cases where TMDC is on top of graphene, which I call S for substrate. Cases where graphene is encapsulating the TMDC, which we call E. And cases where we have the TMDC on top of bilayer graphene, which I call S2. When you're creating these van der Waals heterostructures, you need to take into account that they have different lattice parameters, and then you want to make them commensurate to run the DFT calculation. So then you have some freedom on the twist angle that you add in between them. So we investigated two opposite cases, not opposite, but two different scenarios where one is the 10.9 degree, the other is the 9.1 degree. And what matters in terms of the twist angle is how the K points are folded to the Brillouin zone of the van der Waals heterostructure. And this we can clearly see in the electronic structure that 10 degrees and 19 degrees have different folding of points, and meaning that different interactions between graphene and TMDC. We verified that even though we added graphene, the optical selection rules are preserved. So we have this band brightens up for the A exciton, this band brightens up for the B exciton, same for the 19.1. All these other bands are dark. That's what you would expect. And the exciton wave function is nicely localized at the band edge, very close to the K point. And this explains why you can describe the energy dependence of the TMDC with respect to graphene by the electrostatic effect. But when we looked at the spin and the orbital degrees of freedom, we saw that spins are barely unaffected by the effect of graphene, but the orbital degree of freedom is changing, and specifically for this low energy band here. And this band is actually the one that generates the B exciton. So we found that the A exciton defector is basically unaltered when we have TMDC on graphene, but the B exciton defector can change quite a lot and even change the position with respect to the A exciton defector. And the mechanism behind, the microscopic mechanism behind, is what we call this multi-step process, which, summarizing here in this figure, basically means we have the Dirac cone electrons with very, very large orbital angular momentum. This is transferred to the Q point bands, which are then transferred to the CB minus band. So it's an energy and spin selective coupling that appears in this process. We can verify that this is indeed the Q band character because the composition of the states decrease for the CB minus band and the Q band character increases. So by looking at what kind of orbitals are composing our wave function, we can trace back and generate this multi-step process. Even though there is direct influence of graphene to these states here of the TMDC. And actually the largest contribution, direct contribution of graphene is in the valence band. But we see here that G factors are not effectively altered. And this is because the coupling with graphene does not necessarily mean that it is with the Dirac cone electrons, but somewhere else in the graphene band structure. And we predict that these effects would be suppressed in MO-based materials simply because the Q band is out of resonance, and then you do not have an effective coupling between the Dirac cone electrons in graphene to the Q band of the TMDC. And basically our calculations for some scenarios show that it's barely changing. You don't see any changes in positions. Great, then let's see what happens is instead of applying an external magnetic field, we put the TMDC on top of a magnetic substrate. And basically I will summarize what we have found in these 3 papers here. When we put the TMDC on a magnetic substrate, we're basically creating synthetic magnetic fields via proximity exchange. And basically what it does effectively is to shift the energy bands of TMDC different for spin up and spin down at different K values. And people have indeed observed that. So this is the chromium X3 compound, a ferromagnet in the monolayer limit that was observed in 2017. And then when placing a TMDC on top of that, they did observe that if you are below the Curie temperature of this material, so you're maintaining ferromagnetic order, you really observe a splitting of, here in this case, the trion peak. But essentially, this is connected to these shifts in the band. And more recently, in this publication using other compound, chromium bromide 3, they observed this splitting really in the exciton. So you see sigma plus, sigma minus, different energies without applying any external magnetic field. And we wanted to investigate the microscopics of this effect. So we created structures like this of MOWSE2 on chromium triodine, and we did some twisting, angle analysis, and electric field effects. Basically, what happens is that by twisting, we can see that valence band changes quite a lot in terms of the splitting. This is without spin-orbit coupling for simplicity. And more importantly, that this proximity is very short range, meaning that it only matters the interface, the TMDC and the first chromium triodine. If you have another TMDC on top of the first one, the second one would not carry much of this proximity effect. So meaning that you have a drop of 2 to 3 orders of magnitude. If you place another chromium triodine either in the ferromagnetic ordering or in the antiferromagnetic ordering, you do not enhance the proximity here, again, because of this short-term proximity. And if you place a boron nitride, which typically some people do to preserve the characteristics of the TMDC, you get a drop of, from a milli-electron volt, you go to 10 to the minus 2 milli-electron volts. So for these materials, it's better to not include any boron nitride. And this is the band structure of the heterostructure with spin-orbit coupling. We see TMDC bands here and here, some chromium bands here in the middle, and basically we are looking at optical transitions coming from K and minus K valley or K prime valley around these points here. Basically what we see is that by calculating, taking a DFT, performing an effective modeling on top of that, and then calculating the excitonic spectra, we see that A and B excitons do show a different exciton valley splittings that is dependent on the angle and of course also on the material. And more interestingly, it can be tuned by an external electric field. So you apply a gate voltage in the out of plane direction, you vary your valley splitting by several milli-electron volts. And actually, this has been confirmed experimentally in a smaller range of fields here, close to 0 for us, but indeed, the dependence of the valley Zeeman splitting is linear with respect to the electric field. We kept calculating this kind of structures, and now we have the full picture from 0 to 30 degrees. And what we found is that there's a linear dependence, an increase of the valley splitting as you increase the twist angle, because you are changing the atomic interplay of the ferromagnetic atoms to your TMDC. And again, if you apply an external electric field combined with the twist angle, two things that experimentalists have access to, you can tune from negative values, from something vanishing, a vanishing valley splitting to a valley splitting of tens of milli-electron volts. And perhaps the most interesting thing here is that if you think about a very big heterostructure, one that might be experimentally relevant, all these quantities are varying in space. Here we're showing the values for the exchange splittings we found, and here coding the TMDC atoms with this proximity magnetic moment from the ferromagnet material, and it does change in space, which is something that in the future, hopefully people working on quantum sensing could investigate, and then we would have this magnetic control of magnetism by proximity on the atomic scale. The last heterostructures I want to mention are motivated by the graphene community, where they placed the graphene in a normal ferromagnet, but boron nitride in between. And this was very important to generate very good signals for these transport measurements. And we decided to investigate this kind of structures as well. We put boron nitride in between graphene, in between the TMDC and cobalt nickel. And we see that in this sea of bands coming from cobalt or nickel that are metals, the TMDC bands are nicely isolated here. And this would not be the case if boron nitride was not present. You would completely lose the TMDC character if you place the TMDC on top of cobalt and nickel. And that was exactly what the experimentalists have found for graphene. If you put graphene directly on this metal contacts, you lose the Dirac nature of the electrons. We have also calculated the value splitting. We see large values, and there is one publication that decided to try this kind of heterostructure, but they have used very thick boron nitride layer in between the nickel and the TMDC. This is like maybe 3 to 4 boron nitride layers, and that is too much. That kills completely this proximity exchange. So meaning that they do observe the emission from the TMDC, but no splitting because of the proximity exchange effect. I would like to thank everybody that was involved in this work, and of course the funding agencies. And I hope I have convinced you that transition matter dichalcogenides and their heterostructures are a nice platform to study the spinvalley exciton physics via the valley Zeeman splitting. Thank you very much.
Thank you, Paulo. Thank you very much for a very nice talk. So now we are open for questions. Somebody from home wants to raise a hand or open the mic. So Vilas has a question. Go ahead, Vilas.
Hi. Thanks for the nice talk. I have a couple questions, actually. I work with exons in quantum dots. Mm-hmm. I was quite curious about if there's dark exons in these kind of systems. Dark exons.
In the TMDCs?
Yes.
These are...
At the beginning of the presentation.
Yeah.
Yep. Maybe
so this one here, for instance,
yeah,
they call it dark because the spin expectation value of this band and this band is not the same. But this is perfectly allowed. Of course, they would have a very weak optical matrix element, 2 orders of magnitude smaller than the bright exciton. But they are perfectly visible in the PL spectra because
so they are not completely dark.
They are not completely dark. That was the first name they give, and the TMDC community still carries some of this nomenclature. And nowadays, some people started to call them gray excitons.
Oh, okay. Yeah, because in quantum dots, we have dark exon, and to be able to see them, you have to apply a in-plane or a tilted magnetic field to mix the bands.
Yeah, the same physics would happen here as well. So they are able to measure, not on this works here, but in previous works, they were able to measure the G factor by applying a tilted magnetic field. And then these dark excitons get brighter, and then you observe their features.
And another thing, the lifetime of these excitons they are compared to the quantum dot excitons, or I have no idea.
In the monolayers, there are picoseconds.
Okay, perfect.
The dark exciton maybe hundreds of picoseconds, and the interlayer excitons around nanoseconds.
Okay, so basically it's die quite fast, so it's not possible to pump it coherently.
There are some people that are doing that. I cannot say what is the experimental setup that they really have to probe this kind of things, but they really need this ultra fast pump probe techniques, like some people using femtoseconds to really investigate this kind of coherent dynamics of this kind of materials.
Okay, thank you.
Thank you. Werneck has a question here in the chat.
Yes. Can you read it out loud, the question as well?
Yes. So Werneck is asking, in the context of electronics, the difficulties in controlling transport through valleys independently seems to be now overcome by your way of breaking the valley degeneracy. Could you elaborate a bit on that? Yes, I agree that people are making, let's say, as far as I understand, they're improving the sample quality so that they can really quench this inter-valley scattering times. And then these properties of the valley are more easily observed. I have more knowledge from the optics perspective, and I know that when they started encapsulating the TMDC with the boron nitride, like they did in graphene in 2010 or so, they started to see more interesting phenomena that is related to this quenching of inter-valley scattering. Was that good enough, Werneck?
He said, thank you.
Perfect.
I have two questions for you. So the first one, the contribution to G factor coming from the angular momentum is more or less like 1 over the gap overall, right? Or 1 over, I think it's 1 over the gap, not gap square, but depends on the gap. Mm-hmm. So in your simulations, for instance, if we try gallium arsenide and using LDA, we know that the gap is 0.5, it should be 1.5 electron volts. So then the G factor will be wrong. So you need the gap well described. So which kind of functionals do you use to get good results? This kind of thing.
We used PBE. And indeed, the band gap is underestimated in the TMDCs by roughly 1 electron volt. We also applied the scissor shift to see how the G factors change. The LZ changes with this. They do change by 0.5 or so in this range of 1 electron volt. But the exciton G factor does not change as much. It's nearly constant. Like if we do this, then basically what changes in GC also changes in GV, and this is basically unaffected. So that is one information. For gallium arsenide, I think the thing is more drastic there. If we just use the calculated PBE or LDA band gap, we would be making a much larger mistake, and that we would need to correct with the scissor shift of the band gap. But surprisingly, even though we are using PBE or LDA and the band gap is underestimated, it matches quite well with the experiments. So these are DFT calculated G factors from this summation over bands without correcting the band gap. There are some GW approaches from this paper here. They show that if you use static GW or dynamic GW, then they claim the dynamic GW is more accurate, and that gives nearly the same G factor that you get from the DFT.
I see, but in that case, if you use GW, then you cannot go all the way to the summation of 1,000 bands. 1,000 bands is too much for the GW. So how does that work?
I think in this particular case, they were implementing the derivative with respect to K.
Okay.
And then they could overcome this problem of summing over many bands. I don't know exactly the trick they did, to be honest, because I know some people that say we do the derivative, but in the end they're replaced by the summation over bands.
Okay.
So
the other question is related to something we already talked before. I will not go into details. I guess you're going to understand part of the question from context, but I just want to confirm. So I can, in this picture of the summation, the angular momentum contribution is pretty much the Berry curvature?
Except for some constants and the square here.
Oh, I don't have the square there. Okay.
Yeah, the Berry curvature has a square and another constant here. But let's say if we take the constant out, then the Berry curvature converges way faster than the orbital angular momentum. So we have calculated here in this paper, and I think the Berry curvature converges as soon as you reach 10 bands after the band gap. So this denominator squared really plays a very, very large role.
Okay, I'll talk to you about this later. It's very specific, but thank you. So is there any more questions from here or from the online audience? Guess not. Okay, so if there is no further questions, let's thank Paulo again. So thanks, Paulo. Thanks, everybody, for the audience. And, well, that's it. Thank you, everybody. I'm going to finish the recording here.